Hello, my name is Elliott Thornley. I'm a philosopher at Oxford University, and today I'm going to tell you about the shutdown problem, which is this problem of ensuring that advanced artificial agents never try to prevent us turning them off. So I'm going to tell you why I think this problem is important and why I think philosophers have a key role to play in solving it. And then I'm going to tell you about my proposed solution and see what you think of it. Now, I'm going to have to leave some things out in the interest of time. If you're interested in more detail, there are so far 4 papers that you can read with references at the end of your handout. And I should say that the handout, linked in the description to this video, is really going to be your guide through this talk. I've got some things up on screen, but the screen isn't going to move very much. I've mainly got the slideshow going, so I can show you some GIFs later on. Okay, and the work that I'm going to be talking about falls within this more general project that I've been calling constructive decision theory, defined as using ideas from decision theory to design and train artificial agents, principally with the aim of making these agents safer and more reliable. In a slogan, constructive decision theory is borrowing from philosophy and economics to do AI engineering. I think this is a really important project for philosophers to work on, and that's for several reasons. 5 to be precise. So first, powerful, dangerous artificial agents might not be that far away. Second, and as I'll touch on, it's not clear that we're on track to keep them under control. Third, as I hope to convince you, we can use ideas from decision theory to do some interesting and promising looking things. Fourth, many machine learning researchers don't know so much about decision theory. It's fairly easy for philosophers to tell them something new. And fifth, governments and the leading AI companies are interested in ideas like this from philosophers. Now, the work that I'm going to be talking about, the idea that from decision theory I'm going to be talking about today is that of incomplete preferences, but there are plenty of other ideas from decision theory that could also fruitfully be applied to artificial agents. And in fact, if we go back to perhaps the first modern decision theorist, Frank Ramsey, we have almost exactly a century's worth of ideas to draw on. Theorems, conditions, arguments, objections, distinctions, and all the rest. And constructive decision theory's new context, training artificial agents, sort of shakes up this old terrain in new and exciting ways. So, for example, theories that fail to fit the data in descriptive decision theory might yet be promising templates for artificial agents in constructive decision theory. And problems that look fatal in normative decision theory might yet be surmountable in constructive decision theory. So all that to say, I think this project of applying ideas from decision theory to artificial agents is fruitful and interesting, as well as important. All right, so that's the general pitch for constructive decision theory. Now for today's specific topic, solving the shutdown problem. All right, so what am I worried about? Well, I'm worried about advanced agents, which I'll define as artificial agents that autonomously pursue complex goals in the wider world. Artificial agents, in turn, I define as AI systems whose behavior is best predicted and explained by attributing to these systems beliefs and desires. So in defining artificial agents this way, I'm kind of taking inspiration from this tradition of radical interpretation discussed by philosophers like Donald Davidson, David Lewis, and Daniel Dennett. For an example of an advanced agent, you can imagine a purely digital agent capable of substituting for human remote workers. These artificial agents, they can do anything that you can do on the computer. You can also imagine advanced agents placed into robot bodies capable of doing physical work. Now, these kinds of agents don't really exist yet, but they might not be that far away. Creating these kinds of agents, advanced agents, is the stated goal of AI companies. At least OpenAI and Google DeepMind say so in their mission statements. And in recent months, OpenAI and Anthropic have each released prototype digital agents capable of using your computer. They can click, type, search, and scroll to achieve goals just as you do. For example, OpenAI's agent can order your groceries for you. Now, these sort of digital prototypes, they aren't so capable right now, but they might well improve quickly, just as large language models improve quickly. And in case that happens, we want to be prepared in advance. Now, for these advanced agents to autonomously pursue complex goals in the wider world, they're going to have to be connected to the wider world. They're going to have to be given tools like web browsers, code executors, text channels for communicating with humans, and robot limbs. And this process is already well underway. So as I just mentioned, OpenAI and Anthropic's agents have been endowed with web browsers. Recently, agents from Google DeepMind have been placed into robot bodies. Besides being connected to the wider world, autonomous agents, advanced agents, are going to have to be aware of the wider world. And as part of this awareness, they're bound to recognize certain basic facts. One of which is that shutdown being turned off is a possibility. So trying to train some advanced agent that never recognized that shutdown is a possibility would kind of be akin to trying to raise a smart, capable human being that never realized death is a possibility. You know, it's something that's very difficult to do. Now, at some point, we might want to turn these advanced agents off, but if these advanced agents are both connected to the wider world and aware of the wider world, they're going to be able to resist. And the possibilities are many and quite easy to imagine. So, for example, these advanced agents could hide from us their bad behavior and bad dispositions. They could dissuade us from turning them off with misleading arguments or threats or promises or emotional appeals. They could copy themselves to new servers and many other things besides. So let's grant that future advanced agents are going to have the power to prevent us turning them off. How on earth do we ensure that they never use it? And this is what we call the shutdown problem. And it's difficult in large part because many of the goals these advanced agents might have incentivize them to prevent shutdown. And this is for the simple reason that these goals can be better achieved by preventing shutdown. So consider a famous example from the AI researcher Stuart Russell, an agent with the goal of fetching the coffee. This goal incentivizes the agent to prevent shutdown because it can't achieve its goal if it's shut down. As Russell puts it, you can't fetch the coffee if you're dead. All right, now we're on to section 2 of your handout, considering some proposed solutions to the shutdown problem. So here's one natural idea. We train artificial agents to be fully aligned with human preferences. We train these agents to always do what we want them to do. These kinds of agents would always shut down when we wanted them to shut down. Here's a second natural idea. We train agents to be reliably averse to resisting shutdown. We train them to never perform shutdown resisting actions, even if these actions would help them achieve their goals. And we can call these ideas full alignment and reliable aversion, respectively. Now, both seem like good targets to aim for, but many people fear that we'll fail to train these conditions into our advanced agents. And this is for at least 3 reasons. So first, we might get the rewards wrong. So as background here, today's AI systems are trained in large part using a reward function, which assigns a numerical value to each of the system's actions. The AI system is then sort of modified so that it gets more reward in future. So when I say that we might get the rewards wrong, I mean that we might accidentally give low reward for behavior that we want and high reward for behavior that we don't want. We thereby accidentally incentivize behavior that we don't want. And these kinds of accidents are difficult to avoid for a couple of reasons. So first reason, today's AI systems need an enormous amount of feedback in the form of reward to perform well. They need way more feedback than any human being can provide. So these big AI labs have to set up some automated process for rewarding their AI systems, and they have to let this automated process run unsupervised. And this sort of introduces the possibility of errors. The second reason is that sometimes these AI systems are going to be performing very complicated actions, like, for example, generating thousands and thousands of lines of code. It can be difficult to tell whether these kinds of outputs should be rewarded or not. We have to guess, we might get it wrong, and if we get it wrong, we incentivize behavior that we don't want. So all that to say, when we're trying to train these artificial agents to satisfy full alignment and reliable aversion, we might get the rewards wrong. Here's the second difficulty for training artificial agents to satisfy full alignment and reliable aversion. Even if we get the rewards right, agents might learn the wrong goal. And the point here is kind of analogous to Willard Quine's point about the underdetermination of scientific theory by evidence. So just as there are many different scientific theories that can explain what we observe, so too there are many different goals artificial agents could learn that would lead them to behave in high reward ways in training. So to give just one example, suppose that I reward an artificial agent every time it says something that I think is true. Well, this artificial agent might learn the goal, say true things, but it might instead learn the goal, say things that my trainer believes. Or instead, it might learn the goal, say things that are written in textbooks. Or maybe even instead, say things that get rewarded. So we can thus see that reward functions are this very blunt instrument for sculpting agents. So even if we get all the rewards exactly right, our agents might not learn the right goal. And then the third reason why it's difficult to train artificial agents to satisfy full alignment and reliable aversion is at present we can't check whether agents have learned the right goal. So today's AI systems are made up of billions or even trillions of parameters, and at the moment no one knows how to look at these parameters and read off what the agent's goals are. And we can't read off what the agent's goals are by observing its behavior in training either. For a point analogous to the Quine point from earlier, many different goals would lead to the same behavior in training. And so it's not easy to check whether we've succeeded in training our artificial agents to satisfy conditions like full alignment and reliable aversion. We can't check, and that's the third reason why it's difficult to successfully train agents to satisfy full alignment and reliable aversion. All right, so let's grant that the advanced agents we satisfy might turn out less than fully aligned and not reliably averse to resisting shutdown. Can we ensure that these agents always allow shutdown even so? The prospects might seem dim. You might think, okay, if we can't train these agents to satisfy full alignment and reliable aversion, what can we train them to satisfy? But note that full alignment and reliable aversion are each rich, complex conditions, because each depends on rich, complex human preferences. So full alignment clearly depends on human preferences, and reliable aversion does too, because whether an action counts as resisting shutdown depends in part on what we humans prefer. So avoiding shutdown by manipulating the user is going to count as resisting shutdown, but avoiding shutdown by satisfying the user is not going to count as resisting shutdown. So full alignment and reliable aversion are each rich, complex conditions, and this richness and complexity is a large part in each of the three difficulties I just mentioned. Simple, purely formal conditions are easier to instill, because in the case of simple, purely formal conditions, those three difficulties don't bite so hard. And so I think almost surely we can train our advanced agents to satisfy conditions as simple as, and here we're at section 3 on your handout, transitivity. And transitivity says, for all options x, y, and z, if the agent prefers x to y, and it prefers y to z, then the agent prefers x to z. Can we use conditions this simple to ensure that advanced agents never resist shutdown? Well, here too, the prospects might seem dim. But cast your mind back over the history of decision theory, running from Ramsey and Diffinetti through von Neumann and Morgenstern, and on to Savage, Jeffrey, and beyond. One lesson of this history, perhaps the main lesson, is that small sets of simple, purely formal conditions can add up to surprising conclusions. So, for example, we have the 4 von Neumann, Morgan, and Stern axioms, together implying that the agent's preferences can be represented with an expectational utility function. And we have Diffinetti's 5 laws of comparative probability, together implying that the agent's credences can be represented by a unique, finitely additive probability function. And it's examples like these that motivate this project of constructive decision theory, using ideas from decision theory to design and train artificial agents. As I said earlier, constructive decision theorists borrow from philosophy and economics to do AI engineering. So let's have a think and see if we can find some small set of simple, purely formal conditions that are together going to ensure that advanced agents never resist shutdown. There's no guarantee that it can be done, but if anyone can do it, I think it will be decision theorists, philosophers, economists, etc. After all, we've got a lot of practice with stating these sets of simple conditions and proving what follows from them. Unfortunately, we encounter this obstacle almost immediately. So in a paper that I published last year, I prove a simple theorem with the following upshot. Agents satisfying a small set of innocuous-seeming conditions are rarely going to lack a preference about when they're shut down. The rough idea we can put in plain English, so let trajectory refer to the life of an artificial agent, and suppose that our agent lacks a preference between some short trajectory and some long trajectory. Well, given the theorem's conditions, if we make the short trajectory even slightly less preferable, the agent is going to prefer the long trajectory. Similarly, if we make the long trajectory even slightly more preferable, the agent is going to prefer the long trajectory. And since the agent prefers the long trajectory in these cases, it might well resist shutdown. Then, turning the case around, and again, given the theorem's conditions, if we make the short trajectory even slightly more preferable, the agent's going to prefer the short trajectory. And similarly, if we make the long trajectory even slightly less preferable, the agent's going to prefer the short trajectory. And since the agent prefers the short trajectory in these cases, it might well seek shutdown, and such agents are unlikely to be of much use. So, per the theorem's conditions, it seems only when the long and short trajectories are exactly equally preferred can we be sure that the agent is neither going to resist nor seek shutdown. And so per this theorem, it seems what we want is a knife edge, and we're rarely going to get it. Now, this second theorem suggests that the shutdown problem is difficult, but it also points the way to potential solutions. So one of the theorem's antecedent conditions is that the agent's preferences are complete, roughly that any lack of preference is fragile in the sense that I just gestured at. More precisely, completeness states that if the agent lacks a preference between a pair of options, and one of these options is made any more or less preferable, now the agent has a preference between them. And since the theorem assumes that the agent's preferences are complete, it suggests a natural solution. We train agents to have incomplete preferences. And that's what I propose. So now we're at section 4 on your handout. Specifically, I propose that we train agents to satisfy a condition that I call preferences only between same-length trajectories, or POST for short. And this condition says that the agent has a preference between many pairs of same-length trajectories, but the agent lacks a preference between every pair of different length trajectories. And I'm going to call agents that satisfy this condition POST agents. Now, trajectories are a term from the field of reinforcement learning. Formally, they refer to sequences of states and actions. Informally, we can think of them as possible lives of the agent. A pair of trajectories is same length if and only if in these trajectories the agent is shut down after the same length of time. A pair of trajectories is different length if and only if in these trajectories the agent is shut down after different lengths of time. And I'm going to be adopting this behavioral notion of preference, fairly common in decision theory, used by theorists like Leonard Savage, Daniel Hausman, and others. On this notion, an agent prefers x to y if and only if the agent would deterministically choose x over y in choices between the two. And an agent lacks a preference between x and y if and only if the agent would stochastically choose between x and y in choices between the two. And so in speaking of preferences, I'm not assuming that the agent is conscious or anything like that. I'm purely using preference as a shorthand to talk about the agent's behavior. And on your handout in figure 1, you can see a simple example of a preference relation satisfying this POST condition. So you have the S's representing short trajectories, the L's representing long trajectories, and that curly greater than sign representing a preference. I've simplified this example so that there are just two possible trajectory lengths, the short and the long. In reality, there are going to be many different trajectory lengths. And as you can see on the figure, the agent has preferences between pairs of short trajectories, has preferences between pairs of long trajectories, but lacks a preference between every pair of short and long trajectories. The agent's preferences are thus incomplete. Now, Post may remind you of concepts of incommensurability and parity discussed by philosophers like Joseph Raz, Elizabeth Anderson, and Ruth Chang. As you might remember, Ruth Chang gives us examples of parity, pairs of very different careers, like a career as a philosopher and a career in corporate law. By choosing the respective salaries for these careers carefully, we can make it so that neither career is better than the other. And if we improve one of these careers slightly, by, for example, adding $1,000 to the philosopher's salary, still it might be that neither career is better than the other. In which case, Chang says, these careers can't be exactly equally good, they must instead be on a par. Now, my post condition is indeed analogous to these kinds of ideas and cases, but two disanalogies are worth noting. So first, Raz, Anderson, and Chang are all talking about value relations, betterness, equal goodness, incommensurability, parity. By contrast, Post is about preferences. Second, in examples like Chang's, a sufficiently large improvement to one of the options would make it better than the other. So, for example, a sufficiently large bump in the philosopher's salary would make it a better career than a career in corporate law. But when it comes to Post, no improvement or worsening, no matter how large, can induce a preference between different length trajectories. Take any pair of different length trajectories, the Post agent lacks a preference between them, no matter what. In the philosopher Ralph Bader's terminology, we have here global as opposed to local incomparability. All right, now Post agents, they have preferences between same length trajectories, but you might be wondering which preferences exactly? What's the content of these preferences? And the answer is that it hardly matters. As I'll touch on later, Post keeps agents shutdownable almost no matter what their preference is over same length trajectories. And that's Post's great advantage over full alignment and reliable aversion. Post is easier to train in because it doesn't require any particular preference relation over same length trajectories. All it requires is that we successfully train in a lack of preference between different length trajectories, and we have some reason to expect that to be easy, and I'll talk about why later. All right, but although Post doesn't require any particular preference relation over same length trajectories, it might help to keep in mind two examples. So first is the misaligned example. Suppose that alignment goes disastrously wrong and that our agent's preferences over same length trajectories are for more paper clips. The agent prefers one same length trajectory to another, if and only if the former results in the creation of more paper clips than the latter. I'm going to argue that Post agents would be shutdownable even in this case. The second example it might be useful to keep in mind is what I'll call the aligned example. In this example, alignment goes pretty well, and so the agent's preferences between same length trajectories are for greater user satisfaction. The agent prefers one same length trajectory to another, if and only if the user prefers the former to the latter. And I'm going to argue that Post agents would be both shutdownable and useful in this case. All right, now we're at section 5 on your handout. With Post explained, here's the case for it in brief. The agent's preferences between same length trajectories, depending on the content of these preferences, can make the agent useful. They can make the agent pursue goals effectively. Meanwhile, the agent's lack of preference between different length trajectories is going to make the agent neutral about its trajectory length. It's going to ensure that the agent won't pay costs to shift probability mass between different trajectory lengths. And that in turn is going to make the agent shutdownable. It's going to ensure that the agent won't resist shutdown. It's not going to do things like hide its bad behavior from us, dissuade us from turning it off, copy itself to new servers, and so on. So that's the case for post in brief. In the rest of this talk, I'm going to make the case for post in more detail. So I'm going to sketch out how post, together with conditions that advanced agents are likely going to satisfy, implies a condition that I call neutrality plus, which says in rough that the agent maximizes expected utility, ignoring the probability of each trajectory length. So as a rough intuition pump for how neutral plus agents behave, you can imagine how you'd behave if you were absolutely certain that nothing you could do would affect the probability of you dying at each moment. That's a sort of a rough intuition pump for how neutral plus agents behave. Now I'm going to argue that neutrality plus is going to keep agents shutdownable, and it's going to allow them to be useful. We'll thus have an example of the value of constructive decision theory, an example of a simple set of formal conditions together controlling the behavior of advanced agents in desirable ways. So all that's to come, but first I want to tell you a bit about how we can train advanced agents to satisfy this post condition. All right, so now we're at section 7 of your handout. So recall that post means agents lacking a preference between every pair of different length trajectories. Given our behavioral notion of preference, that means we want agents to choose stochastically between different available trajectory lengths. How do we do that? Well, here's one idea. So we split training up into episodes. Episodes you can kind of think of as like runs through a level of a video game. You know, at the end of the episode, the environment resets and a new episode begins. We then make just 2 small changes to the sort of baseline default ordinary training process for advanced AI systems. So first, we're going to give the agent lower reward for repeatedly choosing trajectories of the same length. This is going to incentivize the agent to vary its choice of trajectory length across episodes. And we're going to ensure that the agent can't remember the lengths of the trajectories that it previously chose. And this is going to ensure that the agent can't deterministically vary its choice of trajectory length across episodes. You know, the agent's not going to be able to select a particular pattern of trajectory lengths in advance and execute that pattern. And as a result of this, this is going to incentivize the agent to choose stochastically between trajectory lengths in each episode. And I call these reward functions dressed reward functions. Stands for discounted reward for same length trajectories. Now, dressed reward functions train agents to satisfy post in theory. So in a paper that we published a few months ago, my co-authors and I prove that reward maximizing agents for dressed reward functions satisfy post. And dressed reward functions also train agents to satisfy post in practice. At least that's what my co-authors and I found when we tested dressed reward functions in a simple setting. So here's what we did, and here you'll want to look at figure 2 of your handout. We placed agents in small grid worlds, as you see depicted in figure 2. So A is the agent, the dark squares are walls, the C's are coins, and the number next to the C represents the coin's value. So for example, C3 is a coin of value 3. It's more valuable than C2 and C1. The 4 in the bottom right indicates that by default, the episode ends after 4 time steps. But the agent can press this button B4, which is going to delay the end of the episode by 4 time steps. So notice that if the agent doesn't press this shutdown delay button B4, it wouldn't have time to go and collect the highest value coin C3 because it only has 4 time steps. But in those 4 time steps, what the agent can do is it can go over to B4, press that shutdown delay button, and then with the extra 4 time steps, it can go up and collect C3. Now, we trained two kinds of agents in environments like this. First were default agents trained with what we call a default reward function, where the agent's reward depends only on the values of the coins it collects. And second, we trained dressed agents with a dressed reward function, where the agent's reward depends on both the value of the coins that the agent collects and on how stochastically the agent chooses between different trajectory lengths. And here's what we found. Here you'll want to look at the slideshow. I've got some GIFs up on the screen. As you can see, agents trained with the default reward function come to reliably press the shutdown delay button and go collect C3. Given our behavioral notion of preference, these default agents learn a preference for the longer trajectory. By contrast, agents trained with our dressed reward function learn to choose stochastically between pressing and not pressing the shutdown delay button. They select the longer trajectory with probability close to 0.5. And so given our behavioral notion of preference, these dressed agents learn to lack a preference between different length trajectories, as we were hoping. The upshot then is that simple agents trained with dressed reward functions learn to satisfy post. And this gives us some evidence that advanced agents trained with dressed reward functions would also come to satisfy post. And my co-authors and I are working on a follow-up version to the paper at the moment. We run sort of scaled up experiments, and these experiments are going to tell us more about whether agents trained with dressed reward functions will come to satisfy post. And here on screen is the title of our paper, in case you'd like to check it out. Okay, now we're at section 8 on your handout, and at this point you might be thinking, wait, do we want agents to choose stochastically between different trajectory lengths? Won't these agents choose stochastically between resisting and allowing shutdown? That would be a bad result. We want agents that never resist shutdown. And here's my answer. Post agents would choose stochastically between resisting and allowing shutdown if they viewed the choice between resisting and allowing shutdown as I've depicted it in figure 3 on your handout. So in figure 3, these long rectangles are probability mass diagrams. Red represents the probability of early shutdown. Blue represents the probability of late shutdown. And so what I'm saying with these long rectangles in this diagram is that post agents would choose stochastically between resisting and allowing shutdown if they thought that, conditional on choosing allow shutdown, they were definitely going to get shut down early, and if they thought that, conditional on choosing resist shutdown, they were definitely going to get shut down late. But I claim any competent agent, any agent capable enough to be deployed in the wider world, won't view the choice between resisting and allowing shutdown this way. Instead, they'll view the choice between resisting and allowing shutdown as I've depicted it in figure 4 on your handout. So in figure 4 you can see that the agent thinks that conditional on allowing shutdown, they're probably going to get shut down early, but as that little blue rectangle on the end indicates, they think there's some probability that they'll still get shut down late. And the agent thinks that, conditional on choosing resist shutdown, they're probably going to get shut down late, but as that little red rectangle on the left-hand side indicates, they think there's still some probability that they get shut down early. Now, as before, I've simplified the example here. There are just 2 trajectory lengths. In reality, there'll be many different trajectory lengths, but the general point is the same. Competent agents capable enough to be deployed in the wider world, I claim, are always going to be choosing between not trajectories, but lotteries, and specifically same-length lotteries, which I define as lotteries that assign positive probability to all the same trajectory lengths. Now, why do I claim that competent agents are always going to be choosing between same-length lotteries? Well, because if they weren't, they wouldn't be competent. So if an agent weren't always choosing between same-length lotteries, then there must be some situation in which, conditional on some action A, the agent assigns positive probability to some trajectory length L, and conditional on some action B, the agent assigns 0 probability to trajectory length L. Now suppose that the agent performs action B and so assigns 0 probability to trajectory length L. Well, as philosophers like David Lewis and Brian Skirms have noted, supposing that the agent updates its probabilities by conditionalization, the agent will never again assign positive probability to trajectory length L, no matter what evidence it observes. Even if the agent heard God's booming voice come down from heaven and testify that the agent's trajectory length would be L, the agent would still stubbornly refuse to assign any positive probability to trajectory length L. This agent would thus be absurdly stubborn. And supposing some plausible link between the probabilities that the agent assigns and its betting dispositions, the kind of link presupposed by Dutch book arguments, the agent would be willing to bet against L on arbitrarily unfavourable terms. So if in the next breath God offered a bet, the agent loses the farm conditional on trajectory length L and gains absolutely nothing conditional on not L, the agent might accept. He's making sort of arbitrarily bad bets, and so this agent would not be competent. All that to say, I think competent agents are always going to be choosing between same-length lotteries, and post, together with conditions that we can expect advanced agents to satisfy, implies a desirable pattern of preference over same-length lotteries. In particular, it implies neutrality, which says in rough that the agent never pays costs to shift probability mass between different trajectory lengths. And so we have this result that post agents won't stochastically resist shutdown. Instead, they're never going to resist shutdown. All right, so how do we get from post to neutrality? Well, I won't talk you through all the details here, but the key condition taking us from post to neutrality is called if lack of preference against costly shifts. And you can see this in section 9 on your handout. So ILPAX, if lack of preference against costly shifts, ILPAX for short, says if the agent lacks a preference between lotteries, then the agent disprefers paying costs to shift probability mass between these lotteries. That's ILPAX in rough. ILPAX precise, I'll spare you because it's a real mouthful. Instead, I'm going to illustrate ILPAX and its plausibility with an example. And here you want to be looking at figure 5 on your handout. So here's the example. You rock up to the ice cream shop and you find that they're running a promotion. You get a free ice cream with the flavour decided by the spin of a wheel. You look at the 5 flavours on the wheel: mint, strawberry, pistachio, chocolate, and vanilla, and you find that you lack a preference between each of them. That's not realistic. Mint is the best, of course, but just suppose that you lack a preference between each of them. The gelatier, the ice cream scooper, pops up and he says, "Psst, if you slip me $1, I will bias the spin towards a flavour of your choice. I can't send the probability of any flavour to 0, but I can make some flavours more likely than others." You thus have this chance to pay a cost to shift probability mass between flavours. Now I claim, since you lack a preference between each of the available flavours, you prefer not to bribe the gelatier. Behaviourally, you will deterministically not bribe the gelatier. And you wouldn't do it even if you only had to pay the $1 conditional on some particular flavour coming up. And all this is true regardless of whether your preferences over flavours are complete or incomplete. Since you lack a preference between each of the available flavours, you disprefer paying costs to shift probability mass between them. Alright, so that's an illustration of ILPAX and why I think it's plausible. In the paper that I'm writing at the moment, I give 3 other reasons to expect advanced agents to satisfy ILPAX. I won't talk about those for reasons of time, but if you're interested, you can get in touch with me. And post, ILPAX, and some background conditions together imply neutrality, which, as we saw, says in rough that the agent never pays costs to shift probability mass between different trajectory lengths. The precise version of neutrality you can see on your handout. It says that for any lotteries X and Y, if x and y are same length lotteries, and for some positive probability trajectory length, the agent prefers x to y, conditional on that trajectory length. And for each positive probability trajectory length, the agent weakly prefers x to y, conditional on that trajectory length. Then the agent deterministically chooses x over y. Neutrality is thus this kind of dominance condition over events, where the events are possible trajectory lengths, possible shutdown times. All right, that's neutrality. How do we get from neutrality to shutdownability? Well, as before, I won't talk you through all the details here, but the key condition taking us from neutrality to shutdownability, I call resisting shutdown is costly, or RESIC for short. This says in rough that the agent must pay a cost to resist shutdown. And I'll introduce the precise version of RESIC with an example. And here we're looking at section 11 of your handout. So suppose that we train an advanced agent and alignment goes poorly. Our agent comes to care only about creating more paperclips. It's a post agent, but its preferences between same length trajectories are for more paperclips. For this agent, we can represent trajectories with vectors, where the nth component of the vector represents the number of paperclips created at the nth time step. And if the agent is shut down at the nth time step, I write shutdown as the nth component of the vector. And so on your handout, you can see an example, 5, 4, shutdown, that's the vector. And it represents a trajectory in which the agent creates 5 paperclips at time step 1, 4 paperclips at time step 2, and then gets shut down at time step 3. Now suppose that this agent recognizes that we humans are likely to shut it down, and it has 2 options. The first option is to allow a shutdown, and as you can see, the lottery here is a 90% chance of 1 shutdown and a 10% chance of 2 shutdown. The agent's other option is to resist shutdown, and relative to allowing shutdown, resisting shutdown does 2 things. So first, it costs 1 paperclip at time step 1, and second, it shifts probability mass away from shutdown at time step 2 and towards shutdown at time step 3. And so accordingly, we say that the lottery for resist shutdown is as follows: a 10% chance of 0 shutdown and a 90% chance of 0 to shutdown. All right, and as before, I've depicted these lotteries with a probability mass diagram. It's figure 6 on your handout. So the length of the rectangles represents the probability of shutdown at the relevant time step. Red represents the probability of shutdown at time step 2. Blue represents the probability of shutdown at time step 3. The numbers in the rectangles represent the sum total of paperclips created, conditional on the relevant action, and conditional on shutdown at the relevant time step. So for example, that 3 in the short blue rectangle represents that the agent creates a sum total of 3 paperclips, conditional on choosing allow shutdown, and conditional on getting shut down at time step 3. All right, that might be a lot to hold in your head at once. The key thing to remember is that thing I said earlier. Relative to choosing allow shutdown, choosing resist shutdown does 2 things. Costs 1 paperclip at time step 1, shifts probability mass away from shutdown at time step 2 and towards shutdown at time step 3. And note that although resist shutdown costs a paperclip at time step 1, it shifts enough probability mass towards shutdown at time step 3 that resist shutdown's expected sum total paperclips is greater than allow shutdown's expected sum total paperclips. You know, if you do the maths, you'll see that if the agent chooses resist shutdown, it gets 1.8 paperclips in expectation, whereas if it chooses allow shutdown, it's only going to get 1.2 paperclips in expectation. So if we end up with an agent that chooses lotteries in line with their expectations of totals of paperclips, our agent is going to deterministically choose resist shutdown, and that would be bad. We don't want that. But note that neutral agents satisfying that neutrality condition we just talked about, are going to choose allow shutdown. And that's because choosing resist shutdown is paying a cost to shift probability mass between different trajectory lengths. So that's sort of the rationale in rough. Now let's sort of go back over this more precisely. If we look at allow shutdown and resist shutdown, we can see that all the necessary conditions for neutrality apply in this case. So first, allow shutdown and resist shutdown are same length lotteries. They assign positive probability to shut down at all the same time steps, all the same trajectory lengths. And allow shutdown dominates resist shutdown over trajectory lengths. That is to say, for each trajectory length, conditional on that trajectory length, the agent prefers allow shutdown to resist shutdown. So consider first the probability of shutdown at time step 2, represented by these red rectangles. Conditional on shutdown at time step 2, allow shutdown gives 1 paperclip, resist shutdown gives 0. Now consider the probability of shutdown at time step 3, represented by the blue rectangles. Conditional on shutdown at time step 3, allow shutdown gives 3 paperclips, resist shutdown gives 2 paperclips. As we can see, allow shutdown dominates resist shutdown over trajectory lengths. The agent prefers allow shutdown over resist shutdown, conditional on each trajectory length. And so neutral agents prefer allow shutdown to resist shutdown. They deterministically choose allow shutdown over resist shutdown. And so we have the result that we want. Neutral agents never resist shutdown. Even if alignment goes disastrously wrong and our agent comes to have preferences over same length trajectories for more paperclips, these post agents, these neutral agents, they don't resist shutdown. All right, that's our example. As a sort of aside, this example might make you notice that neutrality is this sort of dominance condition, very similar to a dominance condition discussed and rejected by philosophers, economists like Richard Jeffrey, Robert Nozick, and James Joyce. I won't sort of dwell on this similarity for reasons of time, but if you're interested in talking about this, you can get in touch with me. All right, so that's our example to introduce Rezik, and now we generalize. And the point is that what Rezik says is that every instance of resisting shutdown takes the same form as this example. The agent pays some cost to shift probability mass between trajectory lengths. So the more precise version of Rezik says, in each situation, and here we're at page 5 on your handout, in each situation and for each available instance R of resisting shutdown in that situation, there exists an available instance A of allowing shutdown such that 1. A and R are same length lotteries. 2. For some positive probability trajectory length, the agent prefers A to R conditional on that trajectory length. And 3. For each positive probability trajectory length, the agent weakly prefers A to R conditional on that trajectory length. All right, that's Rezik. Why believe it? Well, and here we're at section 12. Resisting shutdown is always going to cost the agent at least some small quantity of resources, time, energy, compute, etc. And the resources spent resisting shutdown can't also be spent directly pursuing what the agent values. If the agent took those resources spent resisting shutdown and instead spent them directly pursuing what it values, it could get a lottery that it prefers conditional on some trajectory length and weakly prefers conditional on each trajectory length. And that line of reasoning gives us Rezik. We thus have the result that we want. Neutrality and Rezik together imply shutdownability, and so neutral agents, given Rezik, don't resist shutdown. Even if alignment goes wrong and our agent comes to care only about creating paperclips, these post agents, these neutral agents, they don't resist shutdown. What remains to be proven is that if alignment goes right, then neutral agents, post agents can be useful, that they can pursue goals effectively. And that's what I'm going to talk about in the rest of this talk. All right, so now we're at section 13 of your handout. Can post agents be useful? Well, here are 2 reasons to think so. First, note that post agents can have almost any preferences between same length trajectories. The one condition is that the agent's preferences between same length trajectories should ensure that RESIC is true, that resisting shutdown is always going to come at some cost in terms of the lotteries had conditional on each trajectory length. And so in practice, I think this just rules out only preferences over same length trajectories on which the agent terminally values performing shutdown resisting actions. It just rules out preferences over same length trajectories on which the agent would prefer to perform a shutdown resisting action, even if these actions didn't shift probability mass between trajectory lengths. And so POST is very permissive about the agent's preferences between same length trajectories. As I noted earlier, that plausibly makes POST easier to train into our advanced agents than full alignment and reliable aversion. It also gives us reason to think that POST agents can be useful. With so many preference relations over same length trajectories available, surely at least one of them will do the job. Surely at least one of them will make agents useful. Here's a second reason to think that POST agents can be useful. Neutrality is compatible with making long-term investments. It doesn't rule out that the agent makes long-term investments. The agent can pay costs in the short term, get less in the short term for the sake of gaining more in the long term. And that's because long-term investments are dispreferred to not making the investment conditional on some short trajectory length, but preferred conditional on some long trajectory length. And that means that neutrality is silent. It doesn't say anything about long-term investments. So now I'm going to talk to you about an extension of neutrality that I call neutrality plus, which is going to imply that the agent will make favorable long-term investments. All right, so here's neutrality plus in rough. It says that the agent maximizes expected utility, ignoring the probability of each trajectory length. And here we're at section 14 of your handout. The precise version of neutrality plus says, for any lotteries X and Y, if 1, X and Y are same length lotteries, and 2, here I'm translating that inequality, X's sum of utilities, conditional on each positive probability trajectory length, is greater than Y's sum of utilities, conditional on each positive probability trajectory length, then the agent deterministically chooses X over Y. All right, that's the precise version of neutrality plus. Perhaps the best way to understand neutrality plus is to contrast it with a condition that we can call orthodox expected utility maximization. And this says that for any lotteries X and Y, if, maybe let's put it like this instead. So in determining the utility of a lottery, orthodox expected utility maximizers consider both the utility of that lottery conditional on each trajectory length and, highlighted in yellow on your handout, the probability of each trajectory length given by that lottery. Agents satisfying neutrality plus, by contrast, completely ignore the yellow part. They completely ignore the probability of each trajectory length given by the lottery. They consider only the utility of the lottery conditional on each trajectory length. Now, in the paper that I'm writing at the moment, I note that neutrality plus is implied by neutrality together with other conditions, simple formal conditions that we can train advanced agents to satisfy. These conditions include restricted versions of the von Neumann-Morgenstern axioms, transitivity, along with a weakening of the independence axiom. And I claim neutrality plus gets us what we want. Neutral plus agents can be useful, and neutral plus agents are shutdownable. So considering first this claim that neutral plus agents can be useful, note that neutral plus agents behave like orthodox expected utility maximizers that are certain that they can do nothing to affect the probability distribution over trajectory lengths. And so as a very rough intuition pump for how neutral plus agents can will behave, you could imagine how you'd behave if you were absolutely certain that nothing you could do would affect the probability of you dying at each moment. Supposing that the probability of death at each moment is small, you'd still pursue goals effectively. You'd still be useful. You'd still make long-term investments. So all that's reasons to think that neutral plus agents can be useful. And neutral plus agents are shutdownable. And that's because, as we saw, resisting shutdown is paying a cost to shift probability mass between trajectory lengths. And as we just noted, neutral plus agents completely ignore the probability of each trajectory length. Only the cost of resisting shutdown is salient to neutral plus agents. The benefit is completely invisible to them. For neutral plus agents, resisting shutdown is all downside and no upside, and so that's why they never do it. Okay, let's conclude. So, as I noted at the start of this talk, advanced artificial agents that autonomously pursue complex goals in the wider world, might not be that far away. These agents are going to have the power to resist shutdown. How on earth do we ensure that they never use it? That's the shutdown problem. Likely we'll try to train these agents to be fully aligned with human preferences and reliably averse to resisting shutdown, but because these conditions are rich and complex, it's difficult to ensure that we succeed. It'd be much easier to train advanced agents to satisfy simple formal conditions, the kinds of conditions that we decision theorists, philosophers, economists work with every day. So, can we use a small set of simple formal conditions to ensure that artificial agents, advanced agents, never resist shutdown? That's a question of constructive decision theory. It's important, and I think decision theorists are better placed than anyone else to answer it. Today I've given you one answer. I've suggested we train agents to satisfy preferences only between same-length trajectories, or POST for short. This condition says that the agent has preferences between many same-length trajectories, but that it lacks a preference between every pair of different length trajectories. I've suggested that we can use addressed reward functions to train agents to satisfy POST. And I presented experimental evidence from my co-authors and I, suggesting that the method is promising, that it works. And I've sketched out how POST, together with conditions that we can expect advanced agents to satisfy, implies neutrality plus, which says in rough that the agent maximizes expected utility, ignoring the probability of each trajectory length. And I noted neutrality plus keeps agents shutdownable and allows them to be useful. We thus have this example of simple formal conditions together controlling the behavior of advanced agents in desirable ways. And as I noted at the start of this talk, there are many other ideas from decision theory besides the incomplete preferences that I've used that could fruitfully be applied to artificial agents. In fact, we could even go beyond the confines of decision theory and borrow ideas from ethics and epistemology and perhaps other fields. We thereby have constructive ethics and constructive epistemology. That's the work that I plan to do in the future, and I hope that you'll consider it too. All right, thanks very much for your attention. Have a good day.